13.2, we're looking at saturated solutions and solubility. Uh, this is really the first time we've explored in the class the idea of a dynamic equilibrium. The dynamic equilibrium, in this case, the back and forth are the solute and solvent dissolving to form the solution, and in the reverse of that, the crystallization. This FET-SIM salts and solubility, great job of illustrating that. I use it initially, strontium phosphate, let's name that. How's it going to dissociate? See the ratio of cations to the polyatomic anion. Consider as it's dissolving. What does it mean now to see solid remaining? How many cations are dissolved? How many anions are dissolved? Adding more solid's going to remain in the container. The number of cations and anions stays the same, but it's not static. We see this back and forth dynamic equilibrium. This is the best simulation I know to represent the rates being equal and opposite. Data describing a solubility, the region where it would be unsaturated, the line showing saturation. What happens if we add a certain amount of solute, a certain amount of water at a given temperature? How we reach the line describing the maximum amount of solid that can dissolve as we make our saturated solution. And then this region above, which would be if we're manipulate it to make it supersaturated. There's a lot of demonstrations for supersaturated solutions. I like this one because it shows actual classroom. Jumping ahead with the resulting formation of the sodium acetate crystallizing. Plenty of videos on YouTube for you to choose from. The idea that we add a seed crystal, it initiates the crystallization, and we end up reaching our saturated solution. Considering what happens then at the particle level, what takes place when the solute's first added, when more solute's added, and then what if the amount of solvent is increased? This FET-SIM's great for that. Adding sodium chloride. This would be an example of the sim where you can have quite a bit of the solute dissolve. Will we ever reach a maximum? Adding more and more. Not saturated yet. Okay, eventually saturated. What happens if we now add water? Increase the amount of water. So we can explore that within the sim. Then here's the summary of it. Add in the salt, aqueous, add more, it dissolves, even more. Now we see water, solid sodium chloride remaining, add more water, and eventually add even more, and we'll see that all of the sodium chloride has dissolved once again. Having then as a discussion point, describe these situations as saturated, unsaturated, or supersaturated. How about in which cases do they have the same concentration? Summary of that section. A lot of vocabulary within that. Again, this is, I think, a great example in our first example of looking at a dynamic equilibrium. Factors affecting that. We contrast the behavior of solids with that of gases. My prior knowledge, I'm absolutely thinking about the Gibbs free energy in that section and thinking about how I can introduce some of those ideas and make sense of it for this phenomena. First of all, looking at the axiom like dissolves like. introducing vocabulary for miscible and immiscible, looking at molecules to describe which aspects would be making them miscible, the extended carbon chain versus the hydroxyl group. A little joke, keep the polar bear out of the water. Uh, Looking then at examples where we have similar intermolecular forces, an application of that, making a prediction which cases would be miscible and immiscible. Important idea here is that it's the strength of the intermolecular force is not what's important, it's the type. After all, if you tell me the boiling point, I know the strength of the intermolecular forces. In dodecaine, I think that is the strongest intermolecular forces. It has the highest boiling point. I think in hexane, it's the weakest. So I've intentionally chosen these and given the boiling point data to illustrate it's not the strength of the intermolecular force, it's the type. To sort of illustrate that of what does it mean to see similar intermolecular forces, I sort of contrast this idea of, well, if we take hexane as a solution and we add dodecaine, see if you can spot where I'm adding it. I'm adding more and more, and in each case, I can have very efficient mixing. Taking hexane and adding water to it. It's a lot more difficult. I don't have the same degree of mixing efficiency for the mixing, and in fact, it's better just to keep the two separate. Now, again, my prior knowledge on this, I'm thinking about it in terms of the Gibbs free energy and the energetics for the enthalpy change. And like dissolves like, key idea there is that when you have similar intermolecular forces for the solute and the solvent, in terms of their type, they're taking apart of the solute, they're taking apart the solvent, those endothermic, they're going to lead to very comparable mixing then. It will make it so that the enthalpy change is not very significant. So therefore, it can be, the driving force can be the change in the entropy. Looking again at the structure, describing which one would be more soluble in the water. When we're looking at the temperature effects for the solubility, we're going to contrast the solid and the gas. So looking first of all at the solid, we see that often the solubility increases for the solid with increasing temperature. Not always, but frequently the case. So connecting this back, what's going on with the Gibbs free energy here? If we have something become more spontaneous with increasing temperature, that's because the entropy is increasing during this process. And if it has a temperature dependence, that means it's endothermic. Endothermic because one of the terms is favorable, the other term's unfavorable. So it's telling me generally when I'm dissolving a solid, this is the case. It's typically endothermic, and with the solution formation, the entropy is increasing. By knowing the temperature dependence, I know both the change in the enthalpy and the change in the entropy, the signs for those. When I'm looking at gases, I don't see exceptions. I see as the temperature goes up, the solubility goes down. I can think about that as far as the higher temperatures leading to greater kinetic energy. It's overcoming the solute-solvent interactions. But if I connect it back again with my Gibbs free energy, at the higher temperature, instead of being dissolved, more of it is as the gas. This process then of higher temperature favoring the gas tells me that this equilibrium here, there's an increase in entropy when it goes to be gas rather than dissolved, and that would be an endothermic process. And I can even connect it back here to looking at the different values here for the how soluble they are or not. Something like helium, very weak interactions with the water. Something like CH4, stronger interactions. So that's how I'm making sense of this. We can consider then what happens with the pressure with our dynamic equilibrium, how we can change the rates as we compress it and shift the equilibrium that way. Discussion of Henry's law, application of these. If we're trying to have a lot of dissolved gas, what would be better, N2 or CO2? How about the pressure above it? How about the temperature? So we're looking at the different relationships here. Quick aside, N2 in your beer, if you dissolve that, that's what Guinness has. It's not carbonated, it's a nitro. So if you want to, as a home brewer, maybe you want to add dry ice to the process if you're trying to carbonate it. So we have a lot of different ideas that we're summarizing, a lot of vocabulary within this. And again, this idea with the temperature dependence, really powerful insights in terms of what that means in terms of the enthalpy change and the entropy change. So in this section, part of my goal is to communicate aspects like of that, knowing that we're still going to have a discussion of Gibbs free energy later on. Suggested problems for 13.1, 13.2, and then 13.3.